what is the Big Bang, what happened right after the Big Bang, and what is the cosmic microwave background radiation?
So, the cosmic microwave background radiation is, I always joke that's how I pay the mortgage around here, because the cosmic microwave background taps into our most primal instincts as human beings, not just as scientists, which is that we interpret the world primarily by what we see. Doesn't mean if you're blind you can't interpret it, but let's ignore that. That's an edge case. Let's talk about human beings. So we're born with two refracting, lens-based telescopes in our skulls. Here, if you're listening at home, I'm holding up the telescope again, which has a lens in it. Our eyes have one lens as opposed to the telescope, which has two. That's immaterial. And in the case of the telescopes that we build, we're not looking for optical light in the visible portion of the electromagnetic wavelength, because that's not where the signal that we're looking for resides. Instead, we're looking for heat, because we're looking for the aftermath of the explosive origin of our observable universe. And if that universe had a so-called singularity or a beginning point where in time itself began, it will have very different optical characteristics to a universe that had a cyclical origin. And we can reveal those properties by looking at a property of light, which is very unknown to most people. It's called polarization. So light always has three different properties, two of which are very familiar. The intensity, how bright is this spotlight right over here? That's how intense, how many the photons are and how much energy they have. And then the color is related to the energy, but is really called the spectrum. What is the breakdown by frequency or wavelength of the light that we're receiving? And both of those properties hold true for any electromagnetic wave, from a radio wave to an X-ray. But there's a third property called polarization, which is the orientation of the electric field of the light, what plane it's residing in, or if it has no polarization. It may not have any discernible direction whatsoever. And polarization is kind of like if you and I were to hold a rope. I don't know, where are you right now? Where are you located?
New York City.
So you're in New York City, close to my own old hometown.
Yeah.
So if I shook a rope between you and I, and this was out there, whatever direction, up or down or left and right, that would be the plane at which the rope is polarized. And so too, light has polarization. But again, we're not talking about optical light. We're talking about the oldest light in the universe, called the cosmic microwave background. And this is the relic, the leftover heat. Whenever you make something, when you generate energy from coal or oil, you always have externalities, residuals, and things you don't want. Sometimes that's, carbon dioxide or whatever. But even in the case of nuclear power, which has no carbon dioxide as a byproduct, it still has excess heat that gets released and has to be then, dissipated to a lower temperature reservoir. So there's always an externality. Whenever energy is generated, whenever matter is generated, nuclear fusion, for example, there's an excess left over of heat. And that excess heat that's left over from the formation of the very first elements in the universe's history, namely hydrogen and helium and their isotopes, that has a leftover from that fusion process, a heat that was a result of the formation and the energy that existed before their production. That now has been stretched and cooled off from many, many millions of degrees above absolute zero to just a mere 2.7 degrees above absolute zero. And then upon that signal, we can look for how intense it is, as I said. We can look for its spectral characteristics, how much energy is there versus wavelength. But we can also look for its polarization. And specifically, we look for its polarization as a way to unravel whether or not the universe began with this inflationary singularity. So that it would be imprinted not on the color of the microwaves, if you will, not on the intensity of the microwaves, but exclusively on its polarization properties. So our telescopes from BICEP to the Simons Observatory are primarily concerned with mapping as a function of where you look on the sky, not how bright the microwaves are, not what their colors are, but what their polarization looks like.